Time for another DraftScience video presentation. DraftPhysics.com on the internet in general. Anyway, light photons. So this Huygens Optics guy has made another video, and he's finally asking a question I'm interested in. How big is a visible photon? Unfortunately, after 20 minutes, he really doesn't answer the question, but he does describe another experiment he's done and proposes another explanation that's just a cabal of, again, different pieces of whatever the standard jargon is. And instead of saying something like, we really don't know what it is and we're just guessing and all guesses are equal, or something like that. No, it's just this, we know it's a wave and we know it's this and we know it's that, and that's all, in my opinion. The whole story goes back to Huygens, so it's called Huygens Optics, and that's sort of a giveaway of a bias in perspective. And that was the mistake, in my opinion, is Leibniz and Huygens. Big mistake, in terms of a physics perspective. And people should have stuck with Newton's caution and unwillingness to draw conclusions until he had better evidence. So anyway, I would argue that we do now have enough evidence to draw better conclusions, and they just don't do it. So I'll play this and be provoked to explain many things, and I'll explain them, I think, better.
Hey everyone, have you ever wondered how big a photon of visible light is? It must be smaller than the pupil in your eye, right? In fact, it should be small enough to fit through a 1 micron slit. Yet, it should also be big enough to completely cover 2 slits that are spaced more than 1,000 microns apart.
Alright, so right off the start, we're, again, narrowing based on what we think we're observing, and that's the big mistake. First you have to figure out what a photon is, and if you think it's just a blob, then you're wrong, okay? If you think it's a thing, like a rhinoceros, it's really the guts of the rhinoceros. It's the cells of the rhinoceros. It's the little bits of the photon that make the photon. So, I would argue that this is not a photon, okay? Just photon goes to a place. No, a photon is a series of events. Okay, so it's a series of pieces. Who cares how many? Let's just say there's 4. All right, and that's a photon. So when this happens as an event hitting a surface, 1 event, 2 event, 3 event, 4 event, that's a photon. Now, what we also know about a photon is that it's polarized, that it has a shape in space, and the shape is a line. Okay, so we know that they're going this way, the cells, the bits, and when they hit something, they hit it, like this, it has a length to it, a length this way and a length this way. Okay, it can come this way, this way, this way. That's a wave. So what's hitting the surface, what it's really doing is it's providing a little piece of energy in one location. That little piece of energy is let's say it's the light's hitting the surface perpendicularly. Okay, let's just get rid of this, and then we'll have a little more room. So what does it do? It hits the surface, and it creates energy going into the surface. And you could argue that what's the consequence of that? Well, even if you believed in a wave theory, the consequence would be it's going to push electrons in all these directions. Okay, so the electrons, wherever this photon hits, it's going to hit an electron. It's going to push the electron into the surface. When it pushes it into the surface, it's going to push the other electrons in these kind of directions. And then the next photon hits, and let's say it hits here. Well, let's say it hits here, just to put it on a different line. You can understand these arrows go in all directions. So it hits here, and that means it's creating more energy right behind this energy. So that means it has double energy this way. And then the next one hits, this number 3, and that one's going to hit in line, on this line, and it's going to hit right behind. It's going to give it energy 3, little boosts of energy, and then the 4th one will hit, and that'll give it a final 4th. And the idea is, okay, is that you can understand that these electrons will be going faster and faster as that energy hits in that direction. So it's like hitting a little bullseye in the center, and then the outside ring, and then the outside ring. And the idea is if you do this in one direction, okay, hit here, hit here, hit here, hit here, in a sequence, you know, it's like hitting a car. You hit it in the trunk with a rock, and it moves. And then if you hit it again with another rock, and it moves even faster, and then you hit it again with another rock, and it moves even faster. And that's the quantized aspect of a photon, the discrete pieces of energy. And if the energy comes at the right frequency, it'll push the electrons. Now, each piece of chemistry, you can understand, has the electrons at different distances. And so, therefore, what distance will cause this effect, what frequency, will be different. And that's why different substances reflect light at different frequencies, is because this effect will or will not happen based on the position of the electrons. The timing will be off. So that's why it needs to be a timed event. That's why the frequency is important. That's why its polarization is a real thing. So the real polarization of a photon, so this guy doesn't mention polarization at all, but you can understand it just from polarization. We can know photons are huge, okay? Because the polarization is proportional to the wavelength, okay? So the wavelength, the distance between the bits of the photon, the frequency, the time it takes at the speed of light for the bits to hit the same spot, if you assume reasonably that the polarization is pretty much the same as that wavelength, the wavelength covers 1,000 atoms, and so the polarization is 1,000 atoms. So the size of a photon, that is the whole thing, the whole packet of energy that will be the photon, is huge, thousands of atoms across. So you can't detect a photon with a single atom or a single electron. It has to hit a rather large piece of space, because what is it creating? How do we detect photons? We detect photons by detecting the electricity they create, okay? And we know electricity is a current, and the currents happen in surfaces with atoms. And it's the whole idea of moving an electron across the atom. So, we already have the idea that, electricity isn't made in one atom. So, it could be understood that if you're going to create electricity in something, you're going to have to create it by causing an electron to leave an atom, be an extra electron, and, to create charge. That's how you have to create it. You have to create an electron. So photons are hitting. They're not electrons. They can't charge a surface because they're electrons. So the only way they can charge the surface is to make one of the regular atomic electrons, the ones that are part of an atom. They have to make one of those electrons an extra electron. That's how they charge a surface. All right, so that's probably enough. So I can give you the answer. You want to know how big a photon is? It's big. Okay, it's 1,000 atoms long and 1,000 atoms high, and it's something like this kind of a shape in space. When it comes at you, it's got this kind of shape. It's got like an envelope. It's got a length, okay. It's got no width, okay, and it's got a height. In the sense that the little bits of energy make that shape. So if I've drawn this before, but I mean, if you thought of the envelope flying through space, the quanta of the envelope are here, okay, because they were created by an antenna, essentially, that shot one bit, and then it shot another bit, and then it shot another bit, and it shot another bit as the electricity moved through a surface. So electricity creates photons. Electricity goes through the surface, an atom fires, then another atom fires, then another atom fires, and another atom fires. And that creates the photon. And so, so that's enough to start with. But the question, I think, is answerable, and I think it can be understood if just key things are recognized. The word polarization is really important. It's really part of what a photon is. They all have it. And if you think about what it is, you realize photons have to be composite objects because they have to be very large. The energy hits an electron. the energy inside the photon, little bits of sand inside the photon envelope, hit electrons. But hitting one electron won't make a photon.
So I guess answering this question is not going to be a trivial thing. Now, in the past, I always used to think of a photon as something really tiny, like a little electromagnetic wave traveling through space at incredible speed. But in the last few years, my views have really changed, and in this video, I'll discuss why that is. So if you Google for information about the size of a photon, you will not find one definitive answer. It seems that...
Right, so physics doesn't know the answer because physics really hasn't carefully detailed what a photon is. If they put down on a piece of paper all the things they know about a photon, the things they know, the things that are really certain, not the things like, well, I know it's a wave. No, not that kind of crap. The crap of the effects of themselves and what photons do, and whether or not we ever detect a photon by detecting it perturbating a single atom. Well, no, we never do that. Now, maybe it can, but we never do the experiment because we can't do the experiment. You know, and if you think about how we do the experiments and what we're actually seeing in the experiments, then you can make more rational deductions.
Everybody has their own opinion about this subject, or even about how size should be defined. Some say that because a photon is massless, it does by definition not have size.
I was just silly to say a photon's massless, so you say so. So again, why is this an assumption? Because a photon is massless. Because what? Somebody says so? I mean, it isn't even consistent with their own theory. I mean, they're claiming that photons are twice as bent by gravity, and yet they'll say something like it's massless. How does gravity bend something that's massless? I mean, that's ludicrous right on its face. So, I mean, this is so inconsistent and so stupid. Why would you include that in your argumentation? I mean, why would you even give it any attention to say because a photon is massless? That's never been proven.
Because it does not occupy space like a physical object.
Again, more nonsense. It behaves in every way like a physical object. In every single category, it satisfies the definition of a physical object, in the sense that we can put a piece of dust in a laser beam and we can see the photon bounce off of it, in a sense, and fly into our eyeball. We know that photon didn't get to the target.
But you can also define size as distance or volume over which something interacts with its surroundings, or even with itself.
Well, everything has to be thought of, and, I mean, this is the first rational point, is you say, well, what axioms are we going to agree on? Can we agree on a three-dimensional space and that everything is fitting in the three-dimensional space and its activities happen in the three-dimensional space? I mean, that's what every bit of real evidence indicates is how the universe works. The big things are doing it, we're doing it, and we're going to assume that the little things aren't doing it. That wouldn't be the rational assumption.
And if that's your definition, then photons definitely have size. Now, in school I was taught that a photon is the smallest amount of energy.
Right, and so that was another de Broglie says so. This whole, we're going to define the energy of a photon based on its wavelength, which is only incidentally related to its energy. Its energy is how many little bits of quanta are inside of it, and yes, if the frequency's higher, then there's more of it. If I shoot rain at you at a frequency and I increase the frequency, well, yeah, more rain hits you. Doesn't mean the rain has more, the water has more energy. Just means that obviously I hit you with more because I shot blobs at you more frequently. So what? I mean, it's like saying the energy of water based on water balloons and how fast I throw them at you. They have more energy. They don't have more energy, it's just more water.
That can be present in light of a particular wavelength. So photons do have wavelength, and for physical photons, that wavelength is generally in the order.
Well, this is the duh part. I mean, you didn't know it had a wavelength based on this stupid formula. You knew it had a wavelength because that's how we detected it. So they knew that long before they did this H bar bullshit.
Of half a micron, but wavelength is not the same as size.
Well, it really is. Frankly, in a physical universe, it's how long it takes you to get from point A to point B. And that'll be how much time or volume you're taking up with that event. So if we're saying a photon, if you know, like I said, it's not a huge stretch to say, well, what's a photon? Is it a blob, or is it a composite of events? Even if you believe in a wave theory, what do you think? It's one wave? There, I know its frequency from the one wave. Or do you say, well, yeah, logically it has to be a few waves have to hit for the surface to detect the frequency. How can the surface detect the frequency if I don't hit it with more than one event?
Humans, size is important, I guess. If you buy a new car, you better...
Well, that's usually not what people think about when you say size. They think about other things.
Make sure it's the right size for your family and your garage.
Geez, family. Why would I do that?
And so if you see that the lens can focus light to a spot smaller than a micron, it's tempting to think that a single photon should be smaller than the spot.
Right. So it's smaller than an elephant, but it's bigger than an atom. Yeah.
Right? Because light is made out of photons. Well, things may not be that simple. For one, is that spot size really 1 micron, or is it actually much bigger? One of the most fascinating properties of light is indeed its wavelength. If you look carefully, light constantly reminds us that it must have one. As soon as we create
a frequency. So again, they just always say wavelength. They always try to take away the character of the thing. It's stuff at a frequency, at a period. There, it's just shooting BBs on, off, on, off, on, off. There is something, there's not something. There is something, there's not something. That's a photon.
Disturbance in the path of the light. We can observe this phenomenon called interference. And a very famous example where we can observe interference is, of course, the double slit experiment.
Okay, so unfortunately I'm masking this a little, so we'll move me out of the way. All right, so this is another annoying part, right? Because he's going to do the traditional bullshit, okay, which is, oh, 2 slits and there's 2 vectors and there's, the geometry works. That's the Young analysis, and it doesn't work in the double slit experiment. It doesn't account for the 2 patterns. It doesn't account even for any one of the patterns correctly. It gets the wrong answer, okay? So clearly the math that works recognizes there's 4 sources. So the math that always works looks at the pattern and says the single slit is really the 2 surface experiment, the 2 source experiment. That's the math that works, right? The math that gets the correct answer, no matter how many, you can make 10 slits, you can make 2 slits, you can make any number, and it gets the right answer. That math, okay, Fruntenhauser, or whatever the frick his name is, that math that always works, okay, acknowledges that the single slit is 2 sources, 2 vectors. The double slit, okay, is 4 sources, 4 surfaces, and so on and so on. So it's not 2 paths, it's 4 paths. And the paths just happen to be right on the surface. The wave center would be right on the surface. The surface would be here. The wave would go something like this, with the center of the surface being the center of the wave. Now, also rationally, you can say, well, what's on the surface? Electrons. Maybe the photons are hitting electrons and being scattered. That is, the substance of the photon, the elements of the photon, are each hitting a different electron and going in a different direction. So the composite parts of the photon are being scattered, but they still have the same frequency. They haven't lost their position in space. They still have the same position relative to each other in space. So if you put a screen up, you have a 50-50 chance that they'll go back in closer to in phase versus out of phase. Being in phase and out of phase just is moving things this way. And you have a 50-50 chance that you move them into position versus move them out of position. Being in phase or being out of phase just means you're changing, this little thing here. And it's a 50-50 chance that you stayed in phase or you went out of phase. Out of 50% of phase. Whatever the middle line would be. But this traditional drawing is wrong. It was wrong when Young drew it. It's wrong when everybody does this even the prettier graphics. He still has 2 beams of light coming out of the 2 slit, and it's not 2 beams of light. It's 4 sources. That's the math that works. And that should be emphasized. It's the 4-source experiment. That's a fact. All right? It's not just me saying so. That's a fact. The math that works. The rest of the math doesn't get the right answers.
Where the disturbance in the path of the light is a mask with 2 narrow slits. So here the light can only go along 2 well-defined paths. And the reason
So 2 well-defined paths. No, it's 4 well-defined paths. And that'll give you the right answer. That'll explain both the superimposed patterns. There's 2 patterns, the longest distance between 2 surfaces and the shortest distance between two surfaces. The shortest distance, okay, the fewest number of wavelengths of difference, that's creating the big envelope pattern. And the largest distance, the lots of wavelengths, that's the distance, okay, that's making the little bars. Fact.
The result is that we observe these areas of higher and lower intensities behind the slits. And these areas are where the light waves are either in phase or out of phase.
Right, and being in phase and out of phase is not that complicated. I mean, again, it's all arbitrary where I say, oh, that's out of phase. Well, maybe that's not out of phase. Maybe I have to go all the way to here before it's called out of phase. Yeah, so it's just kind of an arbitrary standard of what exactly the phase has to be. You know, whether each element has to be 564 nanometers. Well, when you see a piece of red light, maybe 2 of the clumps are only 500 nanometers apart, and 2 of the clumps are 600, and 2 of the clumps are some other number. And the fact is the average is the right frequency.
Now, this is just one example. We can also create interference by, for example, recombining the light of a source and its mirror reflection. Or we can even manipulate interference very cleverly by using a Fresnel zone plate pattern.
Right, so I did speed this up a little. Unfortunately, it's 20 minutes long, so I've got to take some liberties. But yes, all that's true. There's different ways of recombining what you're scattering. So, but see, like, no one says the word scatter. So, no one, no one. There's just no one. I'm the only one who's brought it up. That all you're really doing is taking, a stream of bullets, and you're scattering the bullets in different directions. And if you have enough stream of bullets and you scatter all the little bullets, you can just understand that bullets don't go away. They don't die. They're not dead. And all you're doing is saying, can I put the stream of bullets back together again? Can I hit a target with the same pattern that I would have hit it if I never scattered the bullets? And of course you can. 50% of the bullets will recreate a similar pattern.
Interference is caused by the fact that light is an electromagnetic wave or field.
So he says it is. Okay, again, so somewhere they established the existence of these stupid things, these pretend fields, that are just a representation of how the energy is transferred from one object to another object. And it's not some sort of, we saw it, we proved it, we did any of this stuff. It's a crude drawing of on and off. Okay, it doesn't have to be thought of as anything more than there is energy, there isn't energy, there is energy, there isn't energy. And there's certainly no 2 fields, there's just charge. That's all you can do is move electrons. You either did kick an electron out of an atom or you don't kick an electron out of an atom. That's the consequence of all this stuff. And it's a bizarrely vague representation of a concept, just as bent space vaguely represents the idea of a convergence, stuff moving into a planet. But there's a much better explanation for why stuff moves than this explanation. Yet he says it is this thing, like they somewhere really did prove it, and they never really did prove any of this.
And this is the way you generally see alternating electromagnetic fields visualized, as a wave traveling along a narrow line. Now, looking at this kind of depiction,
you're looking at, it makes absolutely no physical sense that anything knows how to do any of this stuff, whatever this is, that anything is physically doing any of this stuff. It doesn't make any sense. The elemental universe isn't made out of this woo. Ugh. It's just a clump, a clump, a clump, a clump, a clump. And now from polarization, we know that the clumps aren't on exactly the same line. They're all flying parallel with each other, but they're not on the same path.
you should ask yourself a few questions. The picture suggests that the perpendicular magnetic and electric fields indicate the field strength as the direction of propagation, but it also suggests that the field travels along a very narrow line. But this is obviously not.
The suggestion that you should say is, well, look, when I drew it, I put more than one of them in here because I really needed to understand how big the wavelength was. I didn't just make one of these things and call it a photon. So a photon is maybe something more composite-y. It takes more than one element of energy to make a photon.
Correct. If only because magnetic field lines are always close.
So, and these field lines, again, is just a misnomer, because what you really want to pay attention to is the lines of force. And what magnets have are lines of force that go out, radiate. Okay, rays of magnetism. And these lines are where there's an equal amount of magnetism. It isn't where nothing travels these stupid lines. Nothing goes along these arrows. If I put a piece of dust here, it won't follow the path of these arrows. There is no arrow. There is nothing moving on these lines. Again, just really bad theory. Flawed. It's really flawed theory, and yet they just write it in the stone. And now forever and ever they have to keep drawing this and saying this is what the field is made out of, when it's not made out of this. It's made out of radiation. Magnets radiate, and what they radiate is a reflection of the universe that's hitting them.
Those loops and extend into space quite a bit, actually quite a bit more than is shown in this picture. And since the electric and magnetic fields are always directly related, we know that the same is true.
Says you, more mush. Blah, 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 blah. No necessity to draw these two fields. There's one field, but there are two forces, okay? Ones that move electrons, the force bits that move electrons, and the force bits that move protons. Photons are made out of the force bits that move electrons.
For the electric field. So even an electromagnetic field with the lowest possible energy, which we might refer to as a photon, can never be this localized entity traveling.
Well, so again, this is just all just mush. None of this should be believed by people. It's just wrong-headed. It's the wrong direction. It's fairy dust. It's bent space. It's a bad answer.
Along a very narrow line. Instead, it must be something widely distributed in space. On the other hand, if we try to detect light, we find that the detection events themselves are very localized, as well as quantized in energy.
Not really. Again, they're not very localized because they're an electrical event, and we can't have an electrical event in a single a single atom. There's no such thing as I connected a wire to a single atom and I produced electricity. So, not true.
We can only detect the field of the light by removing discrete amounts of energy from the field. And when we do this, the process occurs very locally. For example, it can happen when a photon is absorbed in one particular pixel of a CCD sensor. Or should I...
Right, one single pixel, which is many thousands of atoms across.
I say in one particular atom in a pixel of CCD.
So he can say that, but there's no evidence that one particular atom in the sensor detected the photon. We can't see the atoms, we can't tell which atom, we can't any of that. He's just assuming it's one single atom, when it was a series of atoms, okay, that had their electron perturbated, disturbed, and the electron itself left the crystal, traveled along the matrix of the crystal as electricity, and got to our connecting metal that allowed us to detect the charge differential created on the crystal. So again, there's so little detail here that you get this misimpression that somehow we know the photon hit a single atom of the pixel. It never hit a single atom of the crystal. That's not, we don't have any evidence that a single atom is what made the electricity.
Center. So this is where things get a bit weird. On the one hand, we know that the field representing the photon is distributed in space, but when we try to detect it, we can only do so very locally. And we might ask ourselves...
So it's when he says we can only do so very locally, it's just too ambiguous. We can do so over an amount of substance that has to be many hundreds, if not thousands of atoms across. We've never made a sensor that was made out of 4 atoms. We never made a sensor that was made small enough for you to sit there and make a statement that it's very local. So it's very distributed. The fact is you're not going to ever detect a photon with a surface that has less than, 1,000 atoms. I would say it has to have less, it's got to have at least 100,000 for it to work. But anyway.
What do we mean exactly with the term photon? Does it refer to the field or part of the field itself? Or do we refer mostly to the process of transferring energy to and from the field?
And what is energy? Energy should be understood as momentum, but unfortunately, Huygens and Leibniz ruined those concepts. So you broke what energy is as a concept. Energy is a transfer of momentum. Photons have momentum. They have mass, they have a tiny mass, and they have a huge velocity. And they're going to hit things called electrons, generally speaking, and the energy is going to move the electron and give it velocity and momentum, and then that momentum can be increased, and if you give the electron enough momentum, it leaves the atom and creates charge. It charges whatever the atomic substance is by changing the atoms, by changing where the electrons are, either in the atoms or outside of the atoms.
And now that we're asking ourselves all these questions, how long is the electromagnetic wave of a photon? Is it like one wavelength, or approximately 2.5, like shown here, or maybe a few thousand wavelengths? Now, as I said earlier, my views on what photons are have changed quite a bit in the last few years. In fact, there was this one experiment I did in October 2020 that really got me thinking.
Yeah, and his answers are his new vision is even wooier, so that's why it's sort of a downside. I mean, he's done these experiments and now he's reaching for even wooier explanations for photons and their capacity. Instead of thinking it's an elemental universe, it's got to be simple. The mechanical systems have to be simple. Everything that complex evolves. Complexity didn't exist in the origin. It exists in what evolves out of the system. What emerges out of the interactions is where complexity happens. Complexity is a byproduct of interactions. It is not a byproduct of the elements.
I showed this experiment earlier as a side note at the end of a previous video. So what I built was a modified version of the double slit experiment. And the modification I had made was that I had split the path leading to the slits into two spatially separated paths. Each of these paths leads to only one particular slit, and both paths have a different length. In fact, I made the longest path about 40 millimeters longer than the shortest path. And even
right, so it does dispense with any notion of if we know what slit it's going through, now we have a Heisenberg problem. So he destroyed the Heisenberg bullshit, which is a good thing. But you can't be sure of any of this, because even the way he draws this, we put a knife edge here. Well, what does that mean in photon? In photon world, that means, I created diffraction. So I spread the light by putting this knife edge here. I didn't make a clear cut. You can't clearly cut the photon beam with an edge, right? The edge isn't going to work because the edge is a surface, and the surface is going to do what? It's going to scatter light. So it's exactly the opposite effect of what he drew. So what he's assuming happened clearly isn't what happened. So by putting the edge here, he actually diffracted the light. Okay, he actually did scatter it, and he guaranteed that some of this light got into the first slit.
Though 40 millimeters may not sound like much, this distance is equivalent to more than 75,000 wavelengths of the laser light I used. Now, when I brought down the beam power to single photon level, I didn't really know what to expect. But it turned out...
So, why would he even do that? Single photon arguments, again, are just, you're back to an assumption. So if you assume the photon isn't what I'm arguing it is, a composite of very simple thing, just distance between clumps of momentum, then clearly you can understand that the idea of a single photon doesn't mean much, because it's, how many pieces of photon can I have in an environment? Okay, I have no whole photons, but I have millions and billions of pieces of photon. Well, then I'm going to end up having photons. It just depends on how big a surface I try to collect them on.
Experiment still showed very clear interference, even with this additional path difference present. So the experiment suggested that not only can a single photon simultaneously take paths that are spatially separate.
Right, it suggests it, but it doesn't suggest it very loudly because of the complexity. This isn't even what he really did, right? There's more than one beam splitter in the experiment, blah, 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 blah. So it's even more complicated than this drawing in terms of the different interactions that take place and the different things that happen to the photon. So all of these are assumptions. What does the lens do? What does the beam splitter do? As I've pointed out, beam splitters don't create two equal beams. One of them has to go through the little half-silvered matrix, and therefore is going to be diverging along the whole path, and the other one won't be diverging because it didn't go through the little holes. And then we put a mask in, so this doesn't have the mask. Oh, attenuating filter. So what the attenuating filter is a bunch of dark pieces of glass that try to block the light. Well, how does it block the light? Well, it blocks the light by creating, again, more of this. So there's very few paths the photon can get through, right? You're just creating very few straight line paths through the substance where you don't hit an electron. And so what can get through that? Well, only pieces of the photon. So only a piece. The photon is this. Yeah, only one piece gets through. That piece. That gets through. That's it. So you're sending pieces through. So the attenuating filter is just saying, let's filter it into pieces. Just the little pieces of the photon get through. Some pieces of the photon don't get through, some pieces do. And so I'm just sending pieces through, and all I can say is I'm going to argue, all you're really going to do is, where did I recombine the pieces back into a photon? Back into the right polarization and the right sequence.
Separated over a substantial distance, but it also allows these paths to have a very significant difference in length. Now, if you were used to visualize a photon as being a little localized electromagnetic wave, like I used to do, this experiment burns a hole in your brain, because it shows that the interference properties of single photons extend over amazingly long distances in space.
Okay, so he's making this interference, like the interference is extending through space and going through all this. You're just a pattern, on, off, on, off. You're sending on, off this way, you're sending on, off that way, and you're saying, where do the on-offs match? And where do they not? When are they, this one's saying on, off, and this one's saying on, off? You start off the same, you send them through different paths, and all you're doing is saying, where can I collect on, off, rather than on, off, on, some other pattern. You're just looking for the same pattern to be recreated, back in sequence. On, off. That's all you're looking for, is for them both do it at the same time. Both on, both off. Both on, both off. And you're trying to, and the places where you won't see a photon are where they're not in the same sequence, where it's on, and then off.
And at that point, I realized that my ideas about the photon were completely inadequate. And there were several people that told me the outcome of the experiment had to be wrong. Of course, without offering any particular insights on why.
Well, there's lots of reasons why, because you don't know what a laser is, you don't really know what an attenuating filter is, you really don't know what a lens is doing, you really don't know what a beam splitter is doing, you really don't know what this knife edge is doing. Yes, and you really don't understand that the two-slit experiment is the four-surface experiment. So yes, there's lots of reasons why you might not be getting it.
Personally, I'm convinced that the result of the experiment is correct, but I now also think that the explanation I gave for the behavior is flat out wrong. So we're going to do this experiment again, but now stretch that difference in path length a bit further and see what happens.
It's really nice he does these experiments. I wish he would just weigh a stick of butter falling 1 meter. I mean, that would be a really good one to have. And just take the same spring and push two things and see if they move. The fast one can only go 1.4 the velocity. Yeah, go ahead, do those experiments, please. But no.
Will there be interference, no matter how long we make the second path, or will at some point maybe the interference just go away?
So again, the interference is just whether the patterns match. So obviously it wouldn't matter if I'm sending Morse code and I send Morse code 2 inches away from me. And then I send another signal in Morse code all the way around the Earth to get to me. All I'm saying is in the end, does it match? Dot, dash, dot, dash, dot, dash. SOS, whatever. Is it the same message? Is it in alignment? And obviously I can move the 2 inches, 2.1 inch. And now it won't be in alignment. 2.2, oh, it's back in alignment. And 2.3, oh, it's in alignment again. It's just a pattern you're matching. It doesn't. Distance is irrelevant. I could send it to Mars and back. I'm just saying, have I lined up the S and OS, or is the pattern showing up OSO instead of SOS? It's showing up OSO. Yeah, no, I don't have the alignment right.
Let me quickly walk you through the schematic. A helium neon laser produces a beam of coherent monochromatic light, and the intensity of this beam is then attenuated to single photon intensity levels with a series of gray filters. Now later,
Right. So again, and they have no. He won't give you a description of what happens inside of a gray filter. What exactly is happening? How does the photon get through the filter? Oh, well, maybe the photon, the whole thing, the pattern doesn't get through the filter. All that gets through the filter are pieces, and then you can sit on the other side and try to collect a whole photon again out of the different pieces going in all kinds of different directions because they all got scattered by electrons going through the pieces. But anyway.
in this video, I'll discuss how that was done. Next, there's a beam splitter that creates the two paths for the light, and the short path leads directly to the detector while passing a second beam splitter. And the other path takes the beam on a little sightseeing tour and eventually brings the light back.
So again, the beam splitter is cutting the light in half. 50% of the light goes through, and then only 50% gets through here. And then you're putting this, so let's understand there's lots of light going in lots of other directions. There's light going this way, and then there's light going this way.
To recombine with the light from the first path. As you can see, the long path is about 5 times as long as the shortest distance. Now, after the light of the two paths is recombined, it's detected here in a camera where we can look at the interference.
So again, it's not interference, it's just you either recombine into a photon or you don't. You either match the pattern or you don't match it.
Let me show you around the actual setup. Here is the helium neon laser. It's a golden oldie which was produced in December 1979. At its last calibration it was generating less than 1 milliwatt. But wait, does it say in 1985? Now, even though this laser has matured as gracefully as I have in the last 35 years, it's lost quite a lot of its mojo, because now it only produces about 0.3 milliwatts.
So all of this was a bit unnecessary, frankly. Well, we'll just play through it.
But all the better, actually, because we don't need a lot of light for this experiment. Next in the setup, there's a
clearly, if you're trying to make one photon, yeah, you don't need a lot of light.
mirror under 45 degrees that is used to control the beam direction, followed by a set of neutral density filters to bring the power of the laser to single photons.
So this, look at all of this, all these glass slides, and then he's going to say, well, I'm sure when I put this last one in that I achieved one photon per, like every second that passes, there's only one photon in the experiment or something. So he didn't give us any time over which he did the experiment. So when he's collecting the final photon, he didn't tell us whether that's a 5-minute exposure or a 10-minute exposure or that's a half hour of photons. None of that was provided.
Level. The light then passes through a beam splitter, creating the two parts.
Ideally, if you're trying to do an experiment to say you only want one photon in the experiment at a time, you would let the thing go for days. That's how they originally did it in the late 1700s, I think. Might have been the 1800s. Well, whenever they had photographic paper, so it was obviously after photographs were invented. But anyway.
And the first path continues in a straight line to the detector while passing a second beam splitter. And the detector, by the way, is a pretty standard IP camera.
All of this. Let's look again. This is great technology. All of this fancy stuff, and we can't get an experiment to measure how much a stick of butter weighs when it falls a meter. No scientist can do that experiment. And then no scientist can take, the same spring and compress it and put a 1-mass object on it and see how far it goes, and then compress it the same amount and put a 2-mass object, see how far, how fast it leaves. Can't get those experiments done scientifically with this kind of precision.
The Peltier element to reduce thermal noise a bit. The longer path.
So he said a Peltier measurement is he's basically cooling it, so that's what he's using that for. He's electrically cooling the photodetector because the hotter it is, the more random photons it makes, the more noise gets into it.
The setup
it counts heat as photons.
Routed via a Poro prism to the second beam splitter, where it's recombined with the first beam. As you can see, there's also a lens here, which is used to compact the interference pattern a bit to make the detection more sensitive. The additional mirror for the second path was necessary to achieve a detour of more than a meter long on the base plate. By placing the two recombined beams under a very small angle, the interference pattern displays only a few minima and maxima, which is convenient because a pattern like this allows for very sensitive recognition of interference.
But we know it's the double slit he's doing, so it's, we need more pattern to know, did you get the double slit pattern? Did you get the second envelope? Did you get the envelope pattern? So the downside of taking just a narrow portion of the pattern is that now you can't see if it's a double slit pattern. And so there's not just one interference pattern. It's clearly, the point is that double slits create two patterns superimposed.
Even at extremely low intensities. And because the light levels in the room are way too high for doing single photon detection, I also shielded the setup from ambient light. And for this I used a few pieces of cardboard just to give the setup a nice high-tech looking feel.
Right. So, I just make the obvious point that we still don't know if it's a single photon. He's going to go through how he mathematically deduces it is, but his math is based on assumptions about what the photon is and whether you're detecting the same photon you produced or not, or whether you're detecting actually pieces of photons being recombined. And depending on your concept of a photon, that math will mean something or that math will be irrelevant.
Now the most important question in this experiment is, how can you be sure that the beam power of the laser is in the single photon range? Well, imagine that we have a continuous light beam coming out of a laser and we start adding gray filters that each transmit a certain fraction of the light, say.
So the gray filter, the test for the gray filter that might mean something is if they test it not by detecting how many photons hit a surface as whole photons, how many whole photons got through, how much heat got through. So if they measured the heat that transmits through the object, they would be, I think, have a better idea that, there's a lot more energy getting through this thing than what the photons indicate. I didn't put together the same number of photons, but I did get quite a bit of heat energy through the filter. So if you're getting the energy through as heat, you can understand that all you've done is really break the photons. You haven't destroyed the photons. You haven't blocked the photons. You've just turned them into pieces.
10%. At some point, we will reach an output power in the beam that is equivalent to, on average, only a single photon at any time.
So, says you.
So how do we do the calculation? Well, we assume that the light is quantized in discrete amounts of energy. We start out by calculating the maximum lifetime of such a quantum in the setup, given the speed of light and the maximum path length. Now, for 1300 millimeters, this value is 4.3 nanoseconds, which means that for an average of one photon in the beam at any time, the photon flux can be as high as 230 million photons per second. And using the photon energy of the laser light, this flux is equivalent to 74 picowatts. With the current output power of the laser, which is 0.3 milliwatts, we can calculate that we need to attenuate the beam by at least a factor of 4 million to get to this 74 picowatts. And this means that we need a filter with an optical density of 6.6 in the beam. Now, in practice, I was able to detect interference with filters having an optical density of 9.
Right, but the point is so in this is you still have to have an assumption about how long a photon is. And what was his assumption? I don't know.
And if we use this last filter setting, we can calculate that the beam intensity is 250 times lower than that of a beam containing, on average, one photon at any time. So
why don't you just tell me how much time you took to do the experiment? So, that's all. If 5 minutes, if you say 5 minutes, well, then I'm going to say, I don't know if you got single photons. If you said 5 days to get your image, well, then I'm going to be more impressed. The fact is that you're forcing the experiment to take place in less and less time. And doing the experiment in less time means you're more likely to have the energy of more than one photon in the experiment at the same time. And that, again, that's all you need. All you need is the energy of more than one photon to be in the experiment. Pieces of more than one photon to be in the experiment at the same time. And then you're not doing single photon.
Now that we can indeed go into the single photon intensity regime, I can finally show you the result of the experiment. Do we still observe interference with a difference in path of over a meter? Let's not keep you in the dark any longer. This is what we observe.
All right, so we already have some observation of pattern, which, that's not good, right? He's got one of the paths blocked, and we do have pattern. I mean, it's vague, but it's there.
In the single photon regime, if either one of the paths is closed off. And this is what we observe if both paths are open. Now, there's no doubt about it. Even in this case, we observe an interference pattern.
Right. But again, you're observing photons. So the other test would have been, well, what did you observe when you just shot the light at a blank screen? No slits. How many photons did you collect? Was the number of photons you collected when you took the slits out and just detected the light? How many photons did you detect per second? Versus how many did you detect when you put the slits in? I mean, that'll tell you whether you have a single photon or not.
At single photon intensity level, the photons do exhibit interference, even if the paths differ by a length of a factor of more than 5, and in absolute length by more than 1.6 million wavelengths.
Well, like I said, I could send the signal to Mars. I can do a interference, experiment by putting a mirror on Mars, sending a laser beam there, beam splitting and sending it back. All I'm doing is matching a pattern. Okay, the length of time it takes for the pieces to get from one place to another doesn't matter. I can shoot a photon an hour ago. Okay, have it go through some rigmarole, and then send another photon right now. And as long as there's going to be an odds of whether I'm in phase or out of phase, whether the two sources are creating the possibility of recombining in phase. But if I happen to turn it on in one moment, I might get, this one's saying SOS and this one's going to say SOS. And I could turn on another moment and this one will be saying, this will be SOS and this will be OSO. So yeah, the patterns can match or not match. This has nothing to do with interference traveling distance. Nothing at all. You're combining the you're making the pattern on the surface. You're not making it in space.
Now, I can assure you, the more you think about this result, the wackier it gets. And I guess wacky results ask for wacky explanations. So, in the previous video on the subject, I proposed a pretty wacky explanation.
No, so this is what happens with experiments, right? Lots of elements, not really well understood. This is the same thing that goes on in the interferometer, and we get all this bullshit about how they can bounce the photon back and forth 1,600 times at LIGO. And then they can measure these tiny differences, the 1/1,000,000th of a distance of the width of a proton distances or some kind of preposterous nonsense when they don't even know how far the beam went into the mirror 1,600 times. How can they tell how long the beam is when the beam could have gone reflected faster or shorter off the mirror?
In an attempt to explain, I suggested that we could assume that the phenomenon of interference is somehow detached from our temporal and spatial observations.
Jeez. Yeah, that was a really bad suggestion.
Basically, my suggestion was, because light travels with the speed of light, it does not experience time and distance, so all paths are covered instantaneously when viewed from the perspective of the photon. But in retrospect, that explanation is rather silly, and it raises more questions than it answers. Yeah. Also, there is a much simpler explanation that actually makes sense. And this explanation was suggested to me by David Nettlinger, a researcher at Oxford University. He very kindly explained where the experiment went wrong. The physics behind it is pretty hefty, and it's not like YouTube video material, so I'll try to explain this in my own words. The essence is that the electromagnetic field of the beam, after leaving the attenuation filters, is a more or less continuous wave or field, like drawn here schematically. And now you're probably thinking, where is the...
So this is just bullshit they make up, okay? Somehow the amplitude, this is his paraphrase of it, but somehow the amplitude of the signal is changed, and therefore the signal's changed, or it's still SOS, it's still a signal. That's all it is a pattern. You're either going to match the pattern or not match the pattern. So this isn't what happens. If you drew this as your beam's going in, this nice coherent group of photons, and then what's coming out is a bunch of little crap. Okay, little crap comes out.
Quantization. I thought light was made up of individual photons. Well, yeah, but... The thing is that even though the energy transfer processes to and from the field have a quantized nature, the electromagnetic field itself is actually not quantized. It can basically take on any value. So let me explain this in a little more detail.
So he's saying this like this is a real theory, okay? Which, sorry, forget it, okay? Quantization is a pretty well-established fact. And, it goes all the way to the structure of atoms and the facts that, electrons move certain distances and they don't move half that distance. They don't go from here to there. They go, from here or to here. They go certain places, and it's all like connected to magnetism and where you can how you can arrange the magnets to be in balance. There's certain balanced positions, there's certain preferential things, and photons have discrete bits of energy. The point is that the photon is more than one piece of discrete energy.
Contrary to spontaneous emission, which is sort of a random statistical process of energy emission in discrete packages, a continuous laser, like a helium neon laser, emits a beam of coherent light, and the field exiting the laser is a continuous electromagnetic wave which has a high field strength. And that is because almost all the quanta of the energy are added to the beam in phase.
So it's just this is just mush. I don't even know how to paraphrase it. He's saying that the energy is either it's look, you're going, it's up energy or down energy, and there's nothing in between. So it's either all up or all down, or all up or all down, or some kind of crap like that. No, it's either a quanta, no quanta, quanta, no quanta, bit, no bit, bit, no bit, bit, no bit. That's what a photon is.
To the stimulated
A piece of momentum, no momentum. Piece of momentum, no momentum.
emission process. If such a beam passes the Gray filters, it will decrease in intensity because of absorption of a part of the energy in the beam. And yes, this absorption process has a quantized nature, and it happens in discrete steps. But it happens in sort of a random manner in time, and also spread out.
So this drawing, again, just breaks the whole concept, because you're breaking the pattern of the photon. You got SO, 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 O, W, 5, whatever, SO, SOS, blah, 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 blah. I mean, you're breaking the pattern.
Out in space within the volume of the filter. So each absorption event takes sort of a random little bite out of the remaining field, decreasing the intensity a bit. Now, because the electromagnetic field strength itself is not quantized, this process eventually results in a sort of continuous field strength that is much lower than what we would find in a true single photon event produced by spontaneous emission. The field strength can at times even be almost zero or...
Yeah, it doesn't even make any sense. I'm just saying these straight lines in here, this whole thing, you've destroyed the pattern. The photon is the pattern. Without the pattern, there's nothing.
Actually zero. But even though the field is very low, it's still coherent and more or less continuous. So this could very easily explain why we observe interference in this configuration. It's because in essence we have two continuous coherent beams interfering. So yes, the power of the beam is far below single photon intensity level, but nonetheless it's continuous.
So it just doesn't mean anything. Like I said, it doesn't make any sense to me at all. The idea that you just have scattered bits, you take the photon, you break the arrangement, and then you rearrange the rhinoceros, right? You break the rhinoceros into cells, you put it in a transporter beam, right? Little bits of information, and then you reconstruct it on the other side. That's all that's happening. You break a photon, you remake a photon. You break a photon, you remake a photon. You break a photon, you remake a photon. That's all there is.
And this is very counterintuitive if you are taught that light is quantized. So basically I had a poor choice of light source. Had I chosen a fluorescent lamp instead of a laser, my single photon calculation had actually made sense. And of course I would never...
So there's no point in just speculating like that because you don't have a proof and you didn't prove it, so blah 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 blah. Blah blah blah.
Have observed single photon interference in the current setup. The experiment, by the way, also shows a few other interesting aspects of light. You see that the interference pattern consists of these individual sensor pixels that light up, and it's good to realize that these are in fact not single photon detection events. What we see is CMOS pixels that collected a specific minimum number of photons.
Right, exactly, a minimum number of complete photons. So it's just, this is a huge amount of atomic space that this is being viewed on, and there's just no, there's no real point in saying, a photon is either that you say a photon is as big as billions of atoms, or you say a photon is the size of one electron. You can't tell from that. That's not enough information. But yes, I would argue that we're just detecting electricity in the end. So we're not detecting photons. We're detecting where in the crystal electrical charge was created.
And the reason that it is displayed like this is because I cranked up the gain of the camera to a very high level. Anyway, even though we're not observing single photons, we can observe this very interesting phenomenon called shot noise. Basically what we see is that the spatial distribution of photons is not the same for each individual measurement. And this is caused by statistical variations in the photon detection for each measurement.
Well, not really. It's caused by the fact that the photons actually are hitting different places where there's one moment the pattern is recreated here and electricity is created here, and the next minute a little bit of electricity is created here, next minute there's charge created here. Yeah.
It's also a subtle reminder of the fact that we can never observe interference from just a single photon, because demonstrating interference always involves collecting many photon detection events. In other words, what we do when we look at interference is gathering statistical information about the spatial probability of detecting a photon somewhere. And this...
Right, so the longer your experiment takes and the less light that's in it, the more likely you can say, well, it's unlikely that two photons could interact in the experiment at the same time. But, like I said, obviously I'm not going to be impressed with experiments that happen in 5 minutes and you tell me they were single photons. I'm going to say, I don't think so.
Probability itself, like the field, is also not quantized. I guess my main problem with understanding the behavior of light was that everybody always told me that the energy in light is quantized. But they forgot to tell me that the electromagnetic wave, so the carrier of the photon energy...
Oh, so the electromagnetic wave, the wave. Waves are emergent, waves are not elemental. It's just such a mistake. Yuck. Sorry, you're broken your whole view of reality by accepting this Huygens view of reality.
is not quantized. An electromagnetic field can be attenuated, diluted by traveling through space. It can be split into arbitrary fractions when passing a beam splitter. The field has no problem.
So again, they're not arbitrary fractions. They're going to be quite different. The beam splitter does not create two equal beams. The light that goes through the splitter is going to be in a different condition than the light that reflects off the surface. Just like the two-slit experiment. Light that reflects off a surface is not diverging. Light that goes through an aperture is diverging. Very different end results.
Whatsoever with this, because it's not quantized. But of course, the probability of detection being proportional to the square of the field strength will also be diluted or split. And that is basically what we observe when we look at interference. These dark and bright bands we observe are just the result of local variations in field strength.
Okay, so it has nothing to do with the field strength. If they did this with heat, thermally, they would find out that thermally the energy from the photons is hitting all these surfaces equally. There is no pattern. Thermally, it's all the same amount of energy hitting. The same amount of momentum, photonic momentum, is hitting all locations. There is no concentration of it where the pattern hits. OSO is the same as SOS to the surface. The surface couldn't care less. It's real, regardless of phase. Okay, so if they did it with microwaves or something else, you'll find that the same number of microwaves are hitting both surfaces. It's just a matter of jamming with those signals. So in the radio and microwave realm, when you do these experiments, jamming completely explains. Okay, now with photons, we can't say the signals are being jammed, but we can understand that because we don't detect photons based on that. But we could understand that, yes, out of phase is not going to be a visible photon. It's still energy, but it's not a visible photon.
To phase differences between different paths. Now, if you consider the field as the leading property for the probability of detection, the things we observe in diffraction experiments, like for example the double slit experiment, become almost kind of trivial. Because if quantization...
So again, understand that his drawing is trivial. Okay, his drawing is again denying that the math that works has four surfaces in it, not two slits.
is not a property of the field, but just of the energy transfer processes between field and matter. The outcome of the experiment is basically what you would expect. But what is definitely not trivial to imagine is how the energy contained in a wave, spread out in space, can be converted back.
Like I said, yeah, none of that is even imaginable to me. None of it has anything to do with reality. Again, you've never even proven that this little arrow thing has anything to do with anything actually moving in any of those directions. The field is radiation. Everything is radiation. Radiation of little bits of momentum. That's all there is in the universe, is little bits of momentum.
To another form of energy in a very local and quantized event. So to get back to our original question, how big is a photon of visible light? Well, if you consider the photon to be the same thing as the electromagnetic field, photons can be absolutely huge, or at least their volume of interaction can be huge. In fact, within this definition, there is no fundamental limit to its size.
All right, so of course there's a fundamental limit to its size, and then we understand it through the polarization filter. Polarization filters work. They have a spatial relationship, and that relationship is thousands of atoms of separation. So yes, that's the only way you can get a whole photon can't get through. You automatically break it into pieces as soon as you get smaller than a thousand atoms. So if you have a gap that's smaller than 1,000 atoms, you're guaranteed to break that photon. You won't get the original photon will have to get broken. You'll have to make a reconstructed photon. So if you want a whole photon to get through something without having to be broken into pieces and then you having to reconstruct it, The only way you're going to do that is have a gap that's bigger than 1,000 atoms.
But if you define the photon as the quantized interaction between field and matter, then a photon is in fact an extremely localized phenomenon. Now you choose.
Now you choose. I mean, how big is a visible photon? You should have said, I have no clue. Yeah, okay. My clue is you make it up. You decide. I mean, not a very good answer. So anyway, good video in the sense that lots of nice information in there, but some of it just based on these axioms, these assumptions, these presumptions by physics that you have to see it this way. We've proven that it's some wavy, weird thing, and we've proven that there's something called an electric field, whatever the hell that would be. You could sort of get away with magnetic field, but you can't get away with electrical field. Electric is clearly just something that happens inside of wires where you push electrons in the wire. That's electric. There is no electric field. I mean, all you can create is a magnetic field. And again, the magnetic field is just, the consequence of charge. And you're changing the pattern of the radiation. You're changing how much you're going to move electrons versus how much you're going to move protons. And when you do that, you create the different effects of attraction and repulsion. But anyway, enough of video. Did my job. And unfortunately, I won't get it'd be nice if this guy, could do response videos and would interact in some more constructive way, in my opinion, but apparently not. As I did do a video to him before, and I think I'm not sure, but I think he might have blocked me. But whatever. There's no, the internet just, is just not being used to its perfect function, which would be to allow to create the battlefield for ideas, and instead it's going in the opposite direction. Everybody is getting censored. Ideas aren't being fairly challenged, and all the liars are being given free rein, and the truth speakers, the honest folks, are being berated and constantly obliged to defend themselves against endless lies. It's just terrible. Anyway, so till the next time and such. This should be the button, I believe. That was the one. So this has been a DraftScience video presentation. Thank you for your attention and such.